First off, my name is Justin Brooks with Trimble, and I'm joined here with Mike Cook today from TopoDOT. And we'll be talking about the benefits of remote sensing technology, focusing specifically on LiDAR as it relates to power line mapping and inspection. Some of this presentation will be similar to the previous one, but we were going to highlight more of the technology itself and educate on what is at work here and the ability to bring this in-house as opposed to hiring out to a service. A little background on me. I started mechanical engineering at UCF in Orlando and started my career with an industry-leading LiDAR manufacturer. From there, I supported some production-level projects with a large surveying and engineering firm, and now I'm working with Trimble to help increase the utilization of mobile LiDAR systems in the Americas. And for today's presentation, we will start by covering a brief historical background on the North American bulk power system. And this will provide some context on how we came to where we are today. Then we'll do a brief comparison of the traditional and modern solutions for maintaining these electrical systems, leading to our preferred solution and a quick breakdown of what to look for in effective mobile LiDAR systems. Then to wrap up my segment, I'll give a quick overview on the key deliverables that most people are looking for out of these systems. And then that'll provide a great transition for my colleague Mike Cook, who will then outline the various ways to extract intelligence from this LiDAR data captured. So as a brief history, there are over 200,000 miles of high voltage transmission lines in the US alone. This obviously requires a massive effort from multiple disciplines to safely maintain power continuity. Regulatory oversight started around in the 1930s with the Public Utility Holding Company Act. Now Congress passed the PUHCA as a response to shady business practices of huge utility holding companies. These companies controlled utilities in complicated pyramid structures where a few investors at the top held controlling shares of many subsidiary companies below them. So before the PUHCA, there was 3 holding companies in particular that controlled almost half of the entire industry. Now this pyramid structure led to a variety of problems such as inflated rates and hidden charges. And then also, since the holding company was legally separate from the subsidiaries, it was not liable for any debts. So some analysts believe that these abuses greatly contributed to the stock market crash of 1929 and the ensuing depression, which I found interesting. The PUHCA kept things in line for a time, but was eventually repealed by the Energy Policy Act of 2005. This provided tax incentives and loan guarantees for alternative energy production, but it also expanded the jurisdiction of the Federal Energy Regulatory Commission to appoint and oversee a electric reliability organization. Now, these EROs are meant to establish and enforce the reliability standards for the entire US bulk power system. So this led to the North American Electric Reliability Corporation, or the NERC, becoming the first certified ERO in 2006. And now there are over 100 standards that have been developed that cover all aspects of maintenance and reliability of the electrical infrastructure. Now, you guys may be familiar with some of this information already, but in the context of today's presentation, we will be talking about 2 main power line asset classes: transmission and distribution lines. Starting at the power generation plants, electric power is stepped up several thousand volts by transformers and routed through these high voltage transmission lines. These transmission lines are sets of high voltage wires or conductors that carry electric power from the generating plants to substations. Then these substations have other transformers that step the power back down and deliver it to distribution lines. These distribution lines carry power to our individual homes and businesses. Now, the types of structures that are determined by a transmission line's route, it kind of is dependent on the terrain and the existing infrastructure. But generally, as a rule of thumb, the larger the voltage, the bigger the right-of-way necessary, and the further away from the ground the conductors need to be to maintain safe operations. Now, on that note, traditional operations that monitor these lines and the associated infrastructure typically rely on ground patrols of field crews. These guys physically traverse the right-of-way, manually documenting problem areas with photos and taking measurements with instruments such as laser rangefinders. But much of this work is time-consuming and pretty dangerous. However, by utilizing advancements in remote sensing technologies, we could minimize the need to put people in harm's way. So getting into some of these modern solutions, I have outlined some of the most effective tools to rapidly collect, document, and measure right-of-way assets. Many of these have been or will be discussed by other speakers today. So we're going to focus on LiDAR, or essentially light detection and ranging, which has evolved to become a trusted technology to capture 3D information. LiDAR sensors are basically laser rangefinders, shooting out multiple pulses per second. Now on the low end, that could be tens of thousands of pulses per second, and on the high end, that could be up to 1 million or more pulses per second. These measurements create a point cloud, or a 3D model digital twin of the project environment. Once captured, the data can be used to make direct measurements of assets and enable analysts analysis from the safety of an office environment, essentially getting people out of the field. And then after gathering some feedback from end users, it was found that ground mobile LiDAR operations in particular are 2 to 3 times faster, or I'm sorry, 2 to 3 times cheaper than conventional surveys over 1 kilometer, 3 times faster from field to finish, and up to 6 times faster for data collection in the field itself. Now, LiDAR systems are versatile and can be mounted to a variety of platforms, from airborne planes, helicopters, and drones, to ground-based trucks, trains, boats, and UAVs. Now, for transmission lines, airborne and UAV operations are well suited for large projects in hostile terrain, but can be quite expensive when factoring in aircraft rentals. So ground vehicle operations are still popular in areas where the right-of-way is accessible. For distribution lines, ground mobile operations are ideal, as these networks can be complex and reside in populated areas where low and slow flights can be difficult or dangerous. And then for localized line inspections, static, mobile, and UAV LiDAR operations all provide benefits over traditional methods, such as more efficiency, higher safety, and more robust data sets that you can glean intelligence from, which Mike Cook will be talking about here shortly. Now, before I talk about the key deliverables that these systems can provide, I wanted to educate some of the audience that might not be familiar on the individual components that make this technology possible. So here you'll see an example of the premier Trimble MX9 mobile mapping system, but these critical components will apply to all kinematic LiDAR systems, both ground and airborne alike. And the overall accuracy and data quality are determined by the LiDAR sensor and the inertial navigation system. These can basically be thought of as the heart and the brain of the system. Obviously, the laser's max range and precision are key to success, but the INS is equally as important and often overlooked. I won't go too much into the weeds here, but the INS is essentially a navigation device that uses a processor, GNSS, and IMU to continuously calculate the position, orientation, and velocity of your moving object without the need for external references. So in this case, Trimble is utilizing 2 Regal VUX1 HA scanners, each pushing out 1 million points per second in a full 360-degree field of view. And for the IMU, we're utilizing a Planix AP60, taking accurate trajectory measurements at around 200 points per second. And both of these components are well regarded as the best in their class. Now, we're also utilizing 360 spherical cameras and/or spherical cameras that are used to supplement the LiDAR data and pick up details that might not be easily identifiable from the point cloud alone. And specifically to ground vehicles, optional components are often added to maintain high accuracy in GNSS-denied environments. So you can see in the bottom here, the DMI is a wheel-mounted odometer that tracks the distance travel and prevents IMU drift when the vehicle is stopped. And GAMS serves as a secondary offset GNSS antenna for improved heading calculations. Now, all this is brought together on a robust mounting platform that is simple and easy to set up and transport. Now, for all this advanced hardware, you also need some advanced capable software solutions. Here's a brief look at Trimble Mobile Imaging, which encompasses everything you should essentially be looking for in a field collection software. TMI is a simple browser-based interface that can be used with any device with a solid Wi-Fi connection. And it also has the ability to upload background maps and import KML files for project boundaries and/or survey control positions if you need them. Now, mission configuration settings are established during training, so field operators can simply choose the vehicle and project collection profiles from a drop-down menu on the fly. Real-time trajectory tracking and sensor monitoring tools ensure that you're capturing the data you need within your defined accuracy requirements. Now, this software in particular is very easy to use and even easier to train. I mean, crews with little experience are often able to set up the system and start a project within 10 minutes of arriving on scene. Now, I won't go into depth about the best field collection practices today, but feel free to reach out if you'd like to learn more about optimizing your LiDAR data sets. And once this all comes together, the resulting point clouds are photorealistic, high-fidelity 3D models that bring the bulk of the work from the field back to the office. Now, I've highlighted here a few of the key deliverables that can be extracted from the data, and Mike will go into more details with this. But some of the most popular things we see are asset inventories, including classification and geolocation of the assets, conductor span, sag, and clearance analysis, vegetation management, topographic information, conductor and transformer health, and then a bunch of various information for joint use pole audits. Now, at this point, I'd like to introduce Mike Cook from TopoDOT, who will be able to give you more details on how to extract this information you need from the point clouds and then manage all of this data across multiple projects. So, Mike, you could take it away.
Thanks, Justin. Hello, everybody. Welcome to this geospatial event, and obviously thank you, Justin, for leading the conversation here. So I'm about to help you kind of navigate or surf this wave of point cloud data that is coming everybody's way, and I'd like to answer or allow you to kind of answer yourself if you're ready or not for this data. I'm Mike Cook. I'm the lead applications engineer over at TopoDOT. I also hold a bachelor's in mechanical engineering. I've been with the company 10 plus years. I work with the support, the development team, and the sales teams. And obviously I'm not alone. We have a dedicated team to help support this TopoDOT community. And we're essentially a software development company that also provides training, support, and consulting services. So this new wave of data is coming our way, and it's a lot of point cloud data. A lot of organizations and engineering firms have joined this community to provide the best geospatial services they can. And this is going to feed downstream electrical and power operations. Our community has existed for 30 plus years, now with over 500 companies worldwide and 5,000 plus individual users. TopoDOT is an industry-leading software application. We're focused on extracting high-quality topographies, 3D models, assets, and this is all from the point cloud data itself. And again, this is going to feed those downstream operations across multiple disciplines. The primary application areas for TopoDOT include the following: transportation corridors, both rail and roadway, electric and power corridors for transmission, distribution, substations, as well as bridges, tunnels, general structures, and more. Where do we fit into the bigger picture as a company? I will kind of also make a note too. We are a software development company and not technically a service provider. But looking at this workflow here, we could see that the data is collected and registered to control, this was mentioned earlier, at the system level. These are the pink bubbles. This includes static, mobile, and airborne data. From there, the exported point clouds will feed into the TopoDOT process, and these are going to be the green icons. I'll note that the MX9 data is fully compatible with TopoDOT. And here we offer a complete and comprehensive workflow to help manage your data, assess the quality of it, and extract value from your data. And this is done into the format of your choice. This essentially will lead you to the deliverables you're looking for. Now remember, this process works for all data collection types. Point clouds are point clouds. Even if they're mixed or overlapping with each other, it does not matter. First, a quick look at the agenda. I've already given a brief introduction, and I'll dive into three main topics. We'll look at the types of projects out there for outside plant infrastructures, the types of solutions for handling all this point cloud data, such as storage, extraction, viewers. and the big picture. The data is at your fingertips. Collaborate across your organization, extract when you need it, where you need it. So what's actually out there? Well, what we'll look at today is the outside plant infrastructure. So this is, again, transmission lines, distribution lines, and substations. And I've even heard that the electrical grid is the largest machine on Earth. So there's a lot of stuff out there. As long as the feature is large enough and is no smaller than the spacing of data points and or pixels of an image, you'll be able to extract the majority of these features seen here. So let's take a closer look at that. So what features am I talking about? This is a quick list of what you can extract, which includes towers, poles, wires and attachments, clearances, the real estate involved on or between the power and communication space. You could look at encroachment, sag points, footers, etc. The majority of the larger objects can be extracted using the point cloud data alone. And for the smaller objects, you can identify these with the higher resolution imagery along with the point cloud. We'll see one of these images in a moment. So this is the mobile data, and it's a single pass. It's got a dual scanner head configuration, and there's plenty of detail here. We're looking at 2 elevation views of a shared pole with the system's high-res image, and the point cloud here happens to be colorized by elevation. Generally, MLS and TLS provide better detail and quality than airborne systems, which is going to be necessary in order to extract what we see here, as well as all of the features mentioned in the previous slide. Next, we'll show 3 main project types. Transmission lines are generally the easiest to extract and are collected usually by airborne systems. You could technically pull these out or extract or collect with a mobile system as well. But the reason why they're easy is because all the features are isolated and spaced out. They have a consistent wire structure with little change, and they're fairly linear in nature. So a lot of automation routines can handle most transition line projects. Distribution lines are a bit more challenging and require more detail, which makes mobile the ideal system for collection. And the reason why they're a little bit more challenging is because they're surrounded by other features such as trees and light poles. They have inconsistent wire patterns, and they're complex wire routes and paths. Use automation where you can, and finalize with the necessary semi-automated tools to finish the job. In this example, all of the data was collected outside of the substation. Hence, there was no need to shut things down, which will ultimately save time and money. And substations are generally the hardest to extract because they have a variety of equipment and structures, a variety of wire lengths, paths, and all of this is packed into close quarters. Tooling is going to be limited to semi-automation for wires and attachment points and or vertical objects. And I'll note here that it's key to have user-friendly tools to allow for optimal interaction with the point cloud and the imagery. So for example, you want easy navigation. You want to be able to take cross-sections wherever you need to, a variety of cross-sections, as well as snapping to the points, having a variety of options there too, loading closest images, etc. We're all about productivity, and it's important to understand the balance between this automation and user input. There's more value in user-friendly tooling than there is with hands-off automation. Well-defined workflows and user-friendly tooling allows any team to scale effectively. All right, so let's see. what overlapping data looks like. So this here we have a rail project with two data types. You have mobile and UAS LiDAR, courtesy of Trek Design Group. We essentially have data fusion here. The mobile data is used to handle the survey grade accuracies needed within the main rail corridor, while the UAS data is used to handle the remaining outside ground coverage. UAS helps with steep cliffs and or inaccessible locations, and you can apply the same technique to power line mapping. There's flexibility when it comes to exporting all this extracted work. You can export to a combination of formats, shapefiles, CSV, KML, or a JSON file. Or you could just export the full model as a drawing file or CAD file. And this can be used for loading analysis purposes. And another trick is to create drawing sheets to help visualize the displayed work that you've done. This can be seen to the right. In the next few slides, we'll see the strategies behind extraction. Here we'll look at wire and attachment extraction. And the goal here is to vectorize the lines and attachment points with a few simple steps. First, we'll locate the poles and towers using an auto search. Give it a few example poles up front, and then you just basically let it find the rest. So you'll check, add, and subtract as necessary to this tower string here. And then with this pole information, you're going to take it over to wire extraction. And you'll build a wire pattern. Once that pattern or template is set up, this can be used to automate the rest of the extraction. Notice how wires and attachment points are going to be collected at once. All right, so if we need more information on this feature, what we'll use is a tool, which is called the utility tool here. And you're basically going to simply set up a cross-section for a preview. And that preview is going to be of the point cloud. And this is going to automatically center itself and determine pole radius at breast height. You'll get a top-down view of a horizontal data slice and then two elevation views. Within this preview, we can precisely control the tilt, height, top radius, and more. Also, you can use stored templates for fitment, and this will allow you to pull out a variety of measurements. So you can store like the closest imagery, you could store offsets, vertical distances, either from each other or to the ground. All this information can be exported and or displayed graphically, either via a shapefile or a CSV file, like mentioned previously. With this approach, you can extract what's needed much faster than the traditional approach, reducing data collection per pole down to just a few seconds. With the wires and poles extracted, you can now perform an automated encroachment routine. Essentially, this will classify the data around the wires up to a specified radius. In this case, we have two zones to represent an inner and outer region, the inner region being yellow and the outer region being red. And with this data classified, you can then follow up with a clearance to cluster routine, which is basically going to find the closest nearby object, not just a point. So what you'll be left with is a geolocated dimensional element. And we can see that in top view at about 11 feet from that light pole there. What else can be done with this encroachment data? It's usually just a point cloud that has been classified into a specific class ID. We can either save this to an existing point cloud or simply export it to a new one. But sometimes delivering the point cloud is just too much data, or it's not compatible with any downstream operations. Here we could see thousands, if not millions of classified encroachment points. In this case, you can consider a clustering routine which will identify the clusters of data and then basically graphically outline them. What's left is a simple shape element per cluster or object, and this can be seen in top view as a red element or the red elements. This keeps file sizes down and becomes more compatible with those platforms that you're passing this to. And you can also assign attributes such as area or volume to these shapes and then send to Esri or Google Earth. It's basically just line work at that point. Clearances are pretty straightforward. You can gather lowest or at the crown, as well as any crossing wires. You can get the distances between those. And what you'll do is you just simply select your wire of choice and let the tool automatically search for the ground. There's no need to clean up noise or floating points, vehicles, vegetation. As most of the tooling basically filters that stuff out on the fly. And remember the exporting options to a sheet. This is another way to convey field information and measurements. The sheet will include the following. It will include the point cloud, which is represented as a colorized cell or graphic group. Any elements, shapes, lines, and points that you have within the cross-section, and the dimensional elements themselves. You can add the dimensional elements prior to the sheet, or you can do it post sheet creation. And again, this is just another way to reduce the file sizes and become more compatible with those downstream platforms. Remember, we can't always pass the entire point cloud downstream. And unfortunately, we don't have enough time today to cover everything. But what we see here should give you a good idea on what else is possible with your data. It's not just power line data. So, we've focused on power lines for this talk, but there's going to be other needs interconnected, such as topography and asset information within the company or within your company. So how do the benefits of LiDAR span across these operations? So multiple departments can collaborate on top of the process we've just covered. And what you can imagine here is, you're going to have access to data across these operations. You're going to have direct communication with the data experts to extract what you need, where you need it. This is going to reduce survey, design, and construction costs, some by magnitudes of, or orders of magnitude. And the key is to feed these downstream operations into the deliverables they're looking for. And again, you can't just push or hand them off a point cloud. So the foundation of this process so the foundation of this process itself is basically a front-end web portal, which basically puts the data at everyone's fingertips via a simple URL link. So let's see what that looks like. And working together via URL means no software installs that are required. It's basically just a web portal. And all data projects are displayed in an interactive map, which can be seen on the right. And within this web project, you have your 2D line work displayed. You have the control locations, project information, aerial overlays. You have the point cloud itself, which is basically a 2D flattened raster file. And you can display that as height gradient, intensity, or both, or something else. Navigate and view imagery as well on the bottom left there. You could take measurements within this imagery. And this is because the 3D spatial data has been embedded into the photo. This web portal essentially allows all parties involved to review the projects, send markups directly to CAD teams via KMLs, and basically to receive quicker turnarounds and or better geospatial data. Why is all this important? Essentially, it's going to allow you to work remotely with the ease of scalability. The LiDAR technology here applies to all outside plant applications, including inside plant, which I did not cover here. The extracted work is all geolocated, and you're going to have improvements to productivity. You're going to lower costs and reduce those repeat trips to the field. And with the success of this community, the LiDAR market will continue to grow. We've seen projections of up to 3 billion by 2025. And if you have any questions, let's talk either now or offline. And I'll leave you with some of our contact information. You can contact us by either phone, you can visit our website, or email us directly. And if you're into social media, find us there. And I'd like to thank you for your time. So now you can essentially go catch that wave of data coming.
Thank you very much, Mike and Justin. While I'm getting my questions together, let me ask, I think you said that you're a software developer. So, so who uses your products?
So I guess that question is directed towards me. So the people who use our products are going to be a mix of geospatial firms, working with any type of, design engineering firms. So, they might contract that out to those individuals, or they might have their own geospatial group within the, design engineering world to get, the most accurate information they can. So I had flashed a bunch of, logos previously. It's a handful of them, but anybody out there doing design, construction, and you need, that information quick and easy to a high level of accuracy, all of this point cloud data is basically feeding into this demand. So that's where we kind of fit into this big picture.
So I'd like to remind all the attendees, if you haven't done so, to click on the link in your chat box to download the program guidebook, because you can arrange one-on-one video calls with the presenters if you have specific information. So here's a question that came in from Tristan. Looks like it's probably for Mike. Can TopoDOT's encroachment routine perform change detection between multiple data sets over a period of time to monitor growth rates or monitor for new encroachments?
We may not have the tool to tell you the differences over time, but we can at least collect that information for you to do further analysis on it. So technically, if you already have your lines vectorized, you could just sit and reuse those lines over and over on a new data set, which may have larger trees as they're growing. So those outlines that I showed you, the little cluster outlines, or if you're getting a footprint or volume, you can use that information to compare it to previous information that you have. But if it's a huge demand, it's something we can look into with you and help you out with on achieving that final comparison that you're looking for.
So, so here's a question that came in from Paul for Justin. It may be for Mike as well, but Justin, I'll direct it at you first. Are you able to pick up the utility pole tags and similar kinds of information from your mobile LiDAR data, or maybe the combined data that you're picking up as you drive down a road?
That's a great question. And the short answer is yes, but it will depend on how close you can get to that pole, obviously. With some of the imagery that we have and with the options of attaching other high resolution external cameras, you could certainly capture that information if you can get close enough. But with the LiDAR data alone, it kind of depends on the situation. And Mike, I don't know if you can elaborate on that at all.
Yeah, I mean, it's a tough, yeah, it's a tough question, because I mean, if you have the imagery to see that tag, you can, but in reality, you might have a tag behind the pole, you might have vegetation growing on the pole. Data in the real world is just, it's messy. The real world is messy. So what we normally say is pull out what you can, you know, with these newer technologies, and you could still complement it with your traditional methods. If you have to send a team out there to verify a tag, that's definitely possible. And then you can compare both your data sets, you can merge them at the end of the day.
So I have several questions on this whole LiDAR mapping process. So you drive down a road and you pick up all this data magically. Being a surveyor, can you do this without survey control?
So yes, but it depends on what you're trying to extract, right? I mean, if you know, this span and sag analysis and stuff is kind of your primary concern, then it'll be more of the relative accuracies between multiple passes of the point cloud that are more important than the absolute geolocation on Earth, right? So yes, you absolutely can capture a lot of this information without survey control, but if that absolute accuracy and that geolocation within a few centimeters is necessary, then survey control is really the only way to verify that, and then to tie down maybe you know, the points in between kind of the runs.
And so there's a related question to that, because by definition, driving down a power line or driving down a road or driving down a right-of-way is probably the most contradictory in terms of shape for getting good control from a surveying point of view. You have a long linear feature. So what's the best way if you do need good control to do that?
So there's a couple different standards that Caltrans has put out specifically, and Florida Department of Transportation also has some as well. But basically, it will still depend on the environment. But for control spacing, especially if you're trying to get those surveying and engineering grade accuracies, it's recommended to kind of have control between every 750 to every 1,500 feet, maybe with some vertical validation shots in between. Now, and with that type of control distribution, you could pretty confidently get those survey and engineering grade accuracies that you're looking for. Now, even like you mentioned, in a long linear type project, it might be beneficial to also kind of zipper, though, or kind of in a way alternate the side of the right of way that you're putting that control on. So then you can kind of triangulate your position in a much better way there. And we have a couple different tools on the Trimble side, but then also I know, you know, a lot of the other companies do as well, to register the data both down to ground control and then also slam them together for the relative alignment as well. So basically we have a couple different software tools that can account for any different type of situation. And with that, you should be able to match those accuracy requirements you need.
So the basic answer is just because you can drive down a road pretty fast doesn't mean you're done. You might have to still go in. Admittedly, you might be in a vehicle, but stop pretty frequently to set control.
Well, actually, that's a good point as well. So if you have control, if you want to set up control ahead of time and be preemptive with this, then you could have, you know, control targets. But you could also bring this data in first. And if you realize after processing and extracting your information that it's not quite as accurate as you need it to be, you can then go back and shoot in natural features that you can see in the LiDAR point cloud and actually use that as control as well. So yes, I mean, essentially you can set up your control targets ahead of time, or you can use natural features after the fact if you need to continue to tie it down.
Okay, thank you. So here's another question that's come in from Paul. I think it's first for Justin, and I have a feeling it then also requires Mike to add something. So with mobile, how many poles can you pick up, say, in an 8-hour day? And how long would the pre-analytic processing take that is just the processed point cloud?
I guess the short answer there is as fast as you can drive it, right? I mean, even with our, you know, our storage capability on the system is basically set up for 8 hours of continuous collection at the max data rate. So you're only limited by how fast you can drive at that point. Now, with that said, there is really no recommendation for how fast or slow you must drive. But on that note, the slower you go, the higher your density will be and the more detail you'll have from the LiDAR point cloud. So it kind of depends on if you're trying to get as much done as possible in a single day, or if you want some of those, really detailed kind of point clouds as well. And Mike, I don't know if you can elaborate on that as well, on how much you can extract and maybe the time expected to extract that from a registered point cloud.
Yeah, so it's a good question, and it kind of depends on what you exactly need. Like if you just need like the pole location and like a cell at the base versus, including the tilt and like every single attachment point, or if there's a transformer on there, a bunch of attributes that you're adding. I'll say conservatively, if you're kind of in the middle ground of that, we saw kind of the tool previously where, you set up a cross section and you kind of have that view that you pull out all that information. Let's say it's about 1 minute. So in an 8-hour day, you're looking about 500 pulls for, kind of a middle ground of all that information you're looking for. If you're just doing pole locations, it's as easy as just dropping a cell down. It's going to probably double.
Yeah, on that note, and on the processing side, for taking the raw point cloud from the field and visualizing it in your various processing softwares, we tend to fall back on the 1-to-1 ratio for about, depending on your processing machine, of course. But basically, as long as it takes you to drive in the field, it'll probably take you about that amount of time to visualize the LiDAR data set in the office. Now, of course, if you're getting into registration and colorization and things like that, it can take a little more time. But that's a good rule of thumb if you're wondering how much time it'll take to process up front before you even get the data into a point where you can extract the information from.
Okay, thank you. So I'm just going to ask you a quick question here because we're really up on, we are on schedule, so I'm deciding to take you over schedule just a little bit. So try to keep your answer short. Kristen asked, does the mobile LiDAR have a narrow capture band and rely primarily on the INU, I think it means IMU, for stitching the observations together, or is it capturing a wider band for a cloud-to-cloud comparison in combination with the IMU?
I'm not sure I understand that question as well. What do you think he means there?
I was hoping you would understand this better. Mike, any ideas?
Maybe they're talking about kind of like a swath, like you're capturing more data than you need to help maybe register this or do some type of pass-to-pass registration.
Yeah.
So I guess there's a couple of different ways to approach that. And again, I'll try to attack both of them quickly just to answer his question. But basically, the field of view of the scanners are a full 360. So you're not looking at a narrow swath of the ground only, for example. You're going to capture everything around the vehicle. But on that note, the laser footprint itself starts out at, I believe, only a few microns, if not a few, very less than a millimeter separation. But as the laser scan goes further out, that laser footprint will expand. I don't know if he meant the individual laser pulses or the swath of the laser itself, all of the laser points together. But basically, I think it'll be more of, you have the full field of view, but it has a narrow footprint. So you're going to capture everything around you at a at very small details.
Joe, I think you're muted.
Oh, yeah, we lost you there.
I don't want to belabor the point because we're over schedule now, but I think this might be a good discussion for him to have with you guys one-on-one. I'm thinking that maybe he's talking about your two scanner point clouds where they do have overlap and how you register them to each other. So that's just a question. That's just an idea in my head. We really don't have time to get into it. So I'm going to say let's stop here and move on to our next speaker. Thank you again, Justin and Mike.
You're welcome.
Hope you can stick around in case other questions pop up. And I'm going to move on to introducing our next speaker.